Bismillahirrahmanirrahim. Welcome everybody. And today we are going to start the lecture number 9 of the chapter solids. That is about the metallic solids. Now we are going to divide this lecture into four portions. First of all, we will discuss the introduction of the metals and the metallic solids. Then we are going to discuss the metallic bond, properties of metal, and finally the structure of metals. So let us move towards the introduction. Actually, the word metal is from Greek word metallon or from Latin word metallum. And both these words they mean mine or quarry. But mine means that most of the metals they are taken through the mining. So that's why the word metal is related to the mine. Now you are very much familiar with the metals because metals are the majority elements of periodic table. So you can say that most of the elements in the periodic table they are metals. And 95 out of 118 elements in the periodic table they are metals. Out of these 95 there is only one metal that exists at in the form of liquid at the room temperature and pressure, while the remaining 94 they are present in the form of solids. And these are actually the metallic solids that we are going to discuss today. Now, what makes mercury a liquid and the remaining 94 elements a solid? It is actually because of the difference in the strength of metallic bond. So basically the strength of metallic bond is the factor. In mercury the metallic bond is very weak. That's why it is liquid. While in remaining 94 elements the metallic bond is very strong, so they are the metallic solids. So this was the slight introduction about the lecture. Next one is that what is actually the metallic bond? Now the metallic bond is explained by three theories. Electron pool theory or electron C theory, second one VBT, and third one MOT. In this particular lecture, we are going to discuss these two theories, electron pool theory and VBT. So according to electron pool theory, the metal atoms they have very large size. And it is quite evident from their position in the periodic table. The metals are present either at the left, at the middle, or at the bottom of the periodic table. So all the elements that occupy left position, middle, or bottom of the periodic table, they have larger atomic size. And because of their larger atomic size, their valence electrons are not under strong hold of the nucleus. So the valence electrons they get free. And when the valence electrons get free, then the metal atoms they become cations. These are the metallic cations. And here are the free electrons. So these are the free electrons. Now these electrons never stay between any two atoms, but they move in the whole crystal lattice. And as they do not stay between two atoms and they move in the whole crystal lattice, that's why they are called as delocalized electrons. When we use the term localized electrons, it means the electron will stay between the bonded atoms. Just like in case of hydrogen, a single covalent bond is present and there is pair of the bonded electrons, but these bonded electrons stay between the bonded atoms. So these are the localized electrons. While these electrons, they keep on moving in the whole crystal lattice, they do not belong to any single atom or two atoms, they do not stay between the two atoms. So these are called as the delocalized electrons. And the force of attraction which is present between the cations and these free electrons, this force of attraction is actually the metallic bond. You can see that metallic bond is also a non-directional bond. It has multiple directions and in all directions its strength is same. So it is just like ionic bond, it is also a non-directional bond. This is the electron pool theory or electron sea theory, which according to which there is a sea of the free electrons in which the cations are embedded. And the force of attraction between these free or delocalized electron and the cations of the metal, that is called as metallic bond, which is just like ionic bond, a non-directional bond. Now VBT says that metallic bond is actually a covalent bond because these electrons are shared between all the cations, and the bond which is due to the sharing of the electrons, mutual sharing of the electrons, that is the covalent bond. And in fact the d orbitals and p orbitals of the metals, they actually overlap with each other. This overlapping makes the electrons free, and because of this overlapping the metallic bond is called as the covalent bond. But it is not a true covalent bond, just like the covalent bond that we discuss in the hydrogen, fluorine, ammonia, chlorine, etc. In that is not the case. So this is a covalent bond and all these electrons are actually shared between the metallic cations. But this covalent bond is not localized just like this bond. Rather, according to VBT, metallic bond is also a type of the covalent bond, but in this case, it is a delocalized covalent bond. It is not a true covalent bond, I am repeating it. It is just like covalent bond because all these electrons are actually shared between the atoms. So that's why we call it as a delocalized covalent bond. The MOT, when we study in the case of solids, that is called as band theory, and I will try to make a lecture on the metallic bond on the basis of MOT some other time, inshallah. So this one is the electron pool theory and the metallic bond and the nature of the metallic bond. Now keep in mind that electron pool theory is the theory which explains all properties of metals. All properties of the metals, they are explained by this electron pool theory. So if an MCQ is asked in which there is alpha option, electron pool theory, beta, VBT, Charlie, MOT and delta, all of these, let us make a delta all of these. And the question is asked at which of the following theories explains the metallic bond. The correct answer will be all of these. But if the question is raised that which of the following theories explain all the properties of the metal, then the correct answer will be the alpha electron pool theory. Now let us move towards the third part of the lecture, and that is the properties of the metals. The first property the first property that we are going to discuss is the conductivity. And all of you know that metals are excellent conductor of both electricity and heat. And the reason of both these conductivities are the free or mobile electrons. When these electrons move in the crystal lattice, then the current flows. And when we heat the metal at the one end, then the heat induced vibrational energy can easily travel from one side to the other side. These electrons, when the heat is supplied to the metal, these electrons occupy the heat induced vibrational energy, and that vibrational energy is then transferred from one end of the metal towards the other end of the metal. But keep in mind that conductivity of metals, that is inversely related to temperature. It is not directly related. Why? Because when we increase the temperature of the metal, resistance increases. Actually, the amplitude of vibration of these cations increases. Suppose at low temperature the cation is vibrating in this way. This one is at low temperature. So the electrons can easily flow from both sides like this. But when the temperature is increased, now the amplitude of vibration of this cation increases like this. Now it will vibrate with a greater amplitude. Now the electrons, they cannot easily pass from the either side. This creates hindrance to the flow of the electrons, due to which the conductivity decreases. And we may also say that by increasing the temperature, actually the resistance of the metal increases. So this one is the conductivity. And now the best conductor of the periodic table, they are transition metals, and out of transition metal group 1b, that includes copper, silver and gold. These are the best conductor of the electricity in the whole periodic table. That's why you can look around yourself that most of the system of the electricity surrounding you, that is based on these three metals. Either the wires are made up of copper or silver usually. Gold is quite expensive, so it is not used in the electrical works. Why they are best conductor of electricity? The reason is because they have high or greater number of the free electron, especially present in their d orbitals. And what is the order of their electrical conductivity? Again, a very important point. Silver, copper and gold. And the fourth one is aluminium. So these are the four elements of the periodic table with respect to their conductivity. And the best conductor in the periodic table, that is silver. Under the normal conditions, it is regarded as the best conductor of the electricity. So that was about the conductivity of the metal. Now let us move towards the second property, which is lustrous surface. When a metal is freshly cut, or it is freshly polished, or it is freshly prepared, its surface is very bright. This is called as metallic luster. And the reason of this luster is not, listen very carefully, the reason of this luster is not the reflection of light. Because usually when we see some metal, we observe that light falls on the metal and it is being reflected. So that's why the metal looks shiny. But actually the case is not that. The reflection of light is not responsible for the lustrous nature of the metal. Again, the lustrous surface is especially because of these free electrons again. Because when light falls on these free electrons, they move from lower energy to the higher energy. That is called excitation of the electrons. But after spending a short duration of time in the higher energy, they again fall into the lower energy level, and some energy is released, and that photons which are released during the de-excitation of the electrons, they make metals lustrous. But after some time, when the metal is placed in the air, the oxygen of the air oxidizes the surface, the layer of the oxide is usually formed, and the lustrous surface that slowly is tarnished. So the lustrous or the brightness that fades. So this one is the lustrous surface. Now let us move towards the third property. And the third property is metals are malleable and ductile. Now the word malleable is actually from malleus, which means hammer. It means that metals are malleable, they can be hammered, and when they are hammered, they are converted to sheets. They are not brittle like the ionic solids, but they are converted to the sheets. And ductility means that the metals can be forced or shaped into the wires. As you can commonly see the wires of the metals in your surroundings. So the ability to be converted to sheets and wires, that is called as the malleability and ductility of the metals. Why the metals are malleable and ductile? Because the metallic cations, they are in the form of layers. And when we apply pressure on these layers, then these layers slide over each other. And when they slide over each other, this results in the reduction of the thickness of the metal. And when the thickness is reduced, then it can be converted into sheets, and even its shape can be forged into the wires. And not only the slippery nature of the layers or the sliding of the layers over each other is the only factor which is responsible for the ductility and malleability, but there is another factor which is the non-directional nature of the metallic bond. So metals are malleable and ductile because the layers can slide over each other, and second reason is non-directional nature of the metallic bond. The most malleable metal in the periodic table, that is gold, and you know that the gold that can be forged into many shapes when we are talking about the jewelry items. So and let me tell you one thing more very interesting, that during the Rutherford's experiment of the discovery of nucleus, gold foil is used. Why we use the gold foil? Because Rutherford used a foil of the thickness 4 into 10 raised to power minus 5 centimeter. And this kind of thin sheet that cannot be made of any metal except gold because of its maximum malleability. The last one is the fourth and the last one, that is the density. Now metals, they have density from lower to higher value, and the least density belongs to which metal? That is lithium. Lithium is the lightest of all the non-metals, and it is the first solid element of the periodic table as well. And what is density of lithium? It is 0.53 grams per centimeter cube. While the metal having maximum density, that is osmium, and it is almost 22.5 grams per centimeter cube. So we can say that the metals, they range in the density from the very low density of the lithium to the very high density of the osmium. This was the third portion that was about the properties of the metals. Now let's just move towards the last portion of our lecture, which is about the structure of the metals. You know that metals, they have close packing, and when we discuss the structure of the metals, we take metal cations as the hard spheres or the hard balls like. So metals have close packing. And the close packing is of two types, two-dimensional and three-dimensional. When we talk about the two-dimensional close packing, it is again of two types. One is the square packing and other is the hexagonal packing. In case of square packing, the atoms of the metal lie over each other both horizontally as well as vertically. Just like the atoms are lying on each other horizontally and vertically. And the one atom is surrounded by how many atoms are touched by how many atoms. Suppose I am highlighting this atom. It is being touched by 1, 2, 3 and 4 atoms. Now this one is this is not touching it. So 1, 2, 3 and 4 atoms. So in case of square packing, the metal atoms are in such a way that they lie over each other both vertically and horizontally, and each metal atom is in contact with the 4 other metal atoms. And these are the empty spaces which are quite large in this case. These empty spaces are called as interstices, voids, or they may be called as the surfaces. In some books, this square packing is also called as the open structure of metal. And now the next one, that is the closed hexagonal packing, sorry. It is something like this, in which the middle layer, every second layer will be present, or the atoms of every second layer, they will be present in the depression present between the atoms of the first and the third layer. So atoms of the second layer will be present in the depressions between the atoms of the first layer and atoms of the third layer. And the first layer, that will be vertically lying on the third layer. Now in this case, how many atoms touch an atom? Actually, total of the 6 atoms that touch this central atom. This one is the 6th one. Because I'm drawing it with my hand without any, so this also touches this. Actually, I want to say that in this case, the every atoms of the every second layer, they lie in the depressions between the atoms of the first and the third layer, and each atom is in contact with the 6 other atoms. So this packing is relatively more close as compared to, or closer as compared to this one, because in this case the empty spaces will be lesser as compared to the square packing. Now in order to make the three-dimensional structure, which is again of two types, hexagonal close packing and cubic close packing, we are going to retain this hexagonal packing structure, and then we will draw the three-dimensional structure. And in order to discuss the three-dimensional structure of the metal, we will have to place the another layer on these balls or atoms, and then we will place the third layer, and we will see whether the atoms of the second and third layer, they are arranged over the first layer in which fashion. That will be discussed in the three-dimensional structure. So let us talk about the hexagonal close packing and the cubic close packing. Now this one is the close packing. In this diagram, it is quite evident that this atom is being touched by the or surrounded by the six atoms 1, 2, 3, 4, 5, and 6. So the diagram that I drawn before, in that diagram, it was not quite clear that how one atom is being surrounded by the six atom, but in this layer it is quite clear. Now this one is the first layer, and we will represent this first layer with the letter capital letter A. If we want to place the balls of the second layer on this one, then should we place the balls of the second layer on the balls of the first layer, or should we place the balls of the second layer on the depressions or empty spaces of the first layer? So it is a matter of common observation that when we want to place the balls of the second layer, then we cannot place them on the balls of the first layer. Rather, we place them on the depressions or empty spaces between the balls of the first layer. So let us now place the balls of the second layer. So these red ones are the balls of the second layer. When we place the balls of the second layer, now there are two types of the empty spaces. Look at this very carefully. One is this one. This empty space is between the balls, red balls, which are the balls of the second layer. And this one is the empty space between the balls of the second layer. And when we will see through this empty space, we will see the ball of the first layer, the blue ball. And these empty spaces which are present between the balls of the second layer, and when we see through this space, we will not see the ground, rather the balls of the first layer are seen. This is represented with the with the letter A. Similarly, there are some other empty spaces, like you can see that there is an empty space here. Now this is an empty space which is between the balls of the second layer, and this one is also between the balls of the first layer. Mean this one is the empty space which was actually present between the balls of the first layer, and it is not being covered even by the balls of the second layer. So we will show this with the letter B. Now this A is also called as the, because I have already told you that these empty spaces are also called as the void. So this B is called as octahedral void, and A is called as the tetrahedral voids. So B are the octahedral voids. So these are the balls of the second layer. Now we want to place the balls of the third layer. You will have to look at this very carefully and attentively. If we cover this empty space A with the ball of the third layer, it will be placed here at this point. And you can see that this A will be covered and the ball of the third layer will be exactly on the ball of the first layer, on the blue ball. Again, if we want to cover this A, the third ball will be placed here, and it will be exactly on that blue ball, on the ball of the first layer. So when we want to cover the tetrahedral voids or A interstices, then the ball of the third layer will be exactly on the ball of the first layer. Second layer is shown with the letter B. Now look at very carefully that capital A and B, these are for the layers of the balls, and small a and B, these are for the empty spaces. So when A is covered, the ball of third layer will be exactly on the ball of the first layer. That's why we will get an arrangement which will be called as AB, and third layer is again on first layer, so it will be again A, and the fourth layer will be exactly on the second layer, so it will be AB arrangement. And this AB arrangement, that may also be called as the HCP, hexagonal close packing. There are so many metals that show this hexagonal close packing. I will like to mention some example of the metals that show the hexagonal close packing. So examples are beryllium, magnesium, zinc, cadmium, scandium, etc. These are the metals that show hexagonal close packing, in which every third layer is on the first layer. And then a very important question is asked that what are the layers? Number those layers which are exactly over one another in case of this AB arrangement. So repeat this one: AB, 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 and so on. First, second, third, fourth, fifth, sixth, seventh, and eighth. Now look at this. All the layers having odd number, they will be exactly over each other, and all the layers having even number, they will be exactly on each other. So first, third, fifth, seventh, ninth, 11th, 13, and so on, they will lie exactly over each other. In the same way, second, fourth, sixth, eighth, 10th, 12th, they will lie exactly on over the each other. So let us draw this now. It is not difficult to draw this one. Just show the layers. These are the atoms of the A layer, suppose. Then these will be the atoms of the B layer. Again atoms of the A layer. So again atoms of the B layer. And you will repeat it again and again. It will be the hexagonal close packing, or it will be the AB arrangement. Now, this AB arrangement can also be hexagonal, can also be shown like this. Now, these are the atoms of the third layer. These are atoms of the first layer. So you can see that this one is layer A, and then third layer is again A. And in between these two layers, there is layer of another layer of atoms, which is shown something like this. And this one is the B layer. So A, B, A, and again the same repetition of the layers takes place. This is the hexagonal close packing. Now let us move towards the second one. Now in this case of AB arrangement, we covered this empty space A, which is tetrahedral word. Now if you want to place the balls of the third layer, there is not only a single option A, but there is another option, this one, B voids. B voids can also be covered with the balls of the third layer. And if you will cover this B, now the ball will be something like this. Here will be the ball. And you can see that this ball of the third layer is not exactly on this blue ball, any of on these blue balls. So the ball of third layer will not be exactly on the ball of the first layer, but the third layer will be again different one. So if the first layer is A, second layer is B, then the third layer will be C, because that is different from these two layers, A and B. This is called as ABC arrangement of atoms, or it may also be called as the cubic close packing. Now there are so many metals that show this ABC arrangement, just like the copper, gold, platinum, etc. These are the famous metals that follow this structure. Now, in case of ABC layer, what will be the layers that will be exactly lying over each other? So, first, second, third, fourth, fifth, sixth. Now, look at this. The first layer, fourth, seventh, 10th, then 13, and then so on. They will be lying exactly over each other. In the same way, second, fifth, eighth, 11th, and 14th, that will be lying on each other. In the same way, third, sixth, 9, 12, 15, 18, they will be lying on each other. So these two parameters are these two properties, they are very important for MCQs. That what are the layers that exactly lie over each other. Now let us draw this ABC type. Now the balls of the first layer, these are the balls of the first layer, A. This one is second layer, B. And this one is the third layer, C. Again there will be A layer, then B layer, and then C layer. And it will be repeated again and again. So this one is A, B, C, A, B, C arrangement. Or it is also called as the cubic close packing. And this one was A, B, AB arrangement, and it is also called as the hexagonal close packing. So these are the structures of the metals, either hexagonal close packing or cubic close packing. But keep in mind, in both these structures, in both these, the metal atoms will occupy only 74% of the available spaces. 74% of the available space will be occupied by the metal atom, and remaining 26% will be the empty spaces between them. So in both these packings, suppose if 100 meter square is the area available, then 74 meter square will be occupied by the metal atoms, and 26 meter square that will be occupied, or that will be the empty spaces. And if there is 100 meter cube volume, then 74 meter cube is occupied by the metal atom, and 26 meter cube are the empty spaces. So metal atoms, even in their closest packing, they cannot occupy more than 74% of the available space, because the empty spaces are unavoidable. There will be empty spaces whenever the metal atoms will be placed in any arrangement, AB or ABC arrangement. This was all about from the topic of the metallic solids. Next time, inshallah, we will come up with some new lecture. Till then, take care. Allah Hafiz.